In the past few years, we've seen a seismic shift in artificial intelligence, not just in how models perform, but in how they learn, reason, and even reflect on their own behavior. At the heart of this transformation lies a powerful new paradigm: self-consistency. It's not just a tweak to existing methods, it's a fundamental rethinking of how we train and evaluate large language models. Let's start with the basics. Traditional language models operate on a simple principle. Given a prompt, they generate a response by predicting the next word one step at a time. This works well for straightforward tasks, answering questions, writing summaries, translating text, but it starts to falter when we ask for deeper reasoning. Why? Because the model doesn't think, it simulates thought through statistical patterns. It's like a brilliant mimic, not a true reasoner. But what if we could teach a model to check its own work? That's where self-consistency comes in. The idea is deceptively simple. Instead of generating just one answer, the model generates multiple responses to the same question, each one a different reasoning path. Then, it evaluates these answers, identifies the most consistent ones, and selects the one that appears most frequently across the ensemble. This isn't just about voting. It's about exposing contradictions, catching errors, and building confidence through repetition. Let's get technical. Imagine you're asking a model to solve a math problem. If a train leaves station A at 60 mph and another leaves station B at 40 mph, and they're 500 miles apart, when do they meet? A standard model might generate a single chain of reasoning. Distance equals 500, combined speed equals 100 mph, so time equals 5 hours. But what if it made a subtle mistake? Say it divided 500 by 40 instead of 100. It would produce a wrong answer with full confidence. Now, with self-consistency, the model runs multiple sampling paths. One path might say, they're moving toward each other, so speeds add up. Another might say, wait, maybe they're on parallel tracks, so no meeting. A third might correctly calculate. Total closing speed is 100 mph, so 500 divided by 100 equals 5 hours. When we aggregate these, the correct answer appears in multiple chains. The model sees that 5 hours is the most frequent and consistent response. The incorrect one, 5 hours from dividing by 40, only shows up once. So it discards the outlier and selects the consensus. This is where the real power lies. Self-consistency turns randomness into reliability. It leverages the model's internal diversity, not just to generate answers, but to validate them. It's like having a team of experts debate a problem, and the answer that emerges from the most coherent discussion wins. But it's not just about math. This technique shines in complex reasoning tasks, logical puzzles, scientific inference, even multi-step planning. In one study, models using self-consistency outperformed standard decoding by over 15% on the GSM-8K benchmark, where problems require multiple steps of arithmetic and reasoning. And here's the deeper insight. Self-consistency isn't just a post hoc correction. It's a form of implicit metacognition. The model isn't just solving the problem, it's assessing the quality of its own reasoning. It's not saying, I think this is right. It's saying, this answer appears in multiple reasoning paths, so I'm more confident it's correct. This has profound implications for AI safety and reliability. When models can self-correct, we reduce hallucinations, improve consistency, and build trust in their outputs. It's a step towards systems that don't just respond, they reflect. But it's not perfect. Self-consistency works best when the model has enough internal diversity in its reasoning paths. If all paths are biased toward the same error, the consensus will still be wrong. That's why we pair it with techniques like temperature sampling, diverse prompt templates, or even reinforcement learning to encourage exploration. And as models grow larger and more capable, self-consistency becomes even more effective. Larger models have richer internal representations, more varied reasoning strategies, and better calibration, making their consensus more trustworthy. So what does this mean for the future? It means we're moving beyond simple prediction towards systems that reason, evaluate, and improve themselves. Self-consistency is not just a trick, it's a foundational principle in the evolution of intelligent systems. We're no longer just training models to answer questions. We're training them to think better. And that's not just an improvement in performance, it's a shift in what intelligence looks like in machines. The future of AI isn't just smarter models. It's models that can know they're right or wrong. And that perhaps is the first real step toward true machine reasoning.